In this workshop, we are going to learn how to set up the two-way FSI problem in the Ansys workbench. So we will start with a geometry definition. We will create the cylinder of diameter 1 meters. Put the dimensions. Also move the dimension towards the geometry. Now use the extrude command and extrude the geometry by the 20 meters. So basically we are modeling the flow inside the pipe, and this flow will exert the force on the sphere, and in the reaction to their force the sphere will move in the direction of the flow. And for this flow we are going to model the flow with some specified properties of density and the viscosity, and that is based on the Reynolds number of the 1000. So generate. Again double click on the extrude command and use add frozen. This will basically when we create the sphere inside this cylinder, this will not merge that body into the solid of this cylinder. Both bodies will be there with their respective identities, so they are not going to be merged. And we can find out the two boundaries in the ICM CFD and subsequently in the CFD and the FES solver. Now at the length of the 10 meters, that is when flow is expected to be fully developed. So at this location we are going to put the sphere of diameter 0.1 meter. So this time we are going to create the primitives. It should be a sphere. Okay, put the diameter equal to 0.1. So radius is going to be the 0.05 meters. Now move this sphere in the Z direction by the 10 units. And this body should be the head frozen, so that we can have the different boundaries, different geometries at different parts for the sphere and as well as for the cylinder. Generate. Okay, so we are done with the geometry. Now you can save the project, and let's say it's a two-way FSI. So two-way FSI, you can find this file with this tutorial on the YouTube, and link is pasted in the description. All the files will be there. Now insert the ICM CFD module for the meshing. Double click here. So now geometry is with us. Okay, so this was just to confirm that the sphere is with us. Now you can rename this body to the wall of the cylinder. So our just wall. Okay, make it wall. Now next part is sphere, and this will serve as the boundary for the two-way FSI. This boundary is inlet. This one is the outlet. Now change the view to the wireframe. Now we need to set the sizes of the sphere. Now to just calculate the size which we need on different parts of the setup. So just take an example of the sphere. Its diameter is 0.1. So its circumference, like if you take this one, this is going to be equal to the pi d. So 0.1 into 3.14. Now the whole circumference or the circle around the sphere, now it should be resolved at least to represent the geometry properly. And with high resolution, we can even properly solve the flow, field, and flow features along this. So I propose that on the whole cylinder, on the whole sphere, we can start with around 80 nodes around the sphere. So the size is going to be the 0.004. So put this size of the 0.004 on the sphere and just right click on the surfaces and click on tetra sizes to be just confirm about the size we are putting on the their particular boundary. So as you can see, this size seems okay for the sphere, but once we generate this mesh, we can change the size later on in this session. Okay, now the next thing is the size on the inlet and the outlet boundary. So put a 1 point here at the 50% location and find the distance between 2 points, that is like this should be equal to the 1. So it's a 1. So again use same formula, that is pi d. So this time it's going to be the diameter is 1 into 3.14, and because it's an inlet boundary, so high resolution is not necessary, but at least it should be enough to represent the geometry or resolve the geometry properly. So I propose around 40 points. The size is 0.0875, or roughly speaking the size should be the 0.00 sorry, 0.08. The size is going to be the 0.08, and same is the true for the outlet boundary. Apply. Now this is going to be the size on this boundary. Now because the wall of the cylinder, this one, has a length of the 20 meters, so we want to divide this by the, let's say, 100 point. The size is going to be the 0.2 on the wall. It's a 0.2. Apply and generate the tetra mesh with the option robust octree. The robust octree method is useful because it does not require the surface mesh to be input for the generation of the volume mesh. But this has a problem of size of next size would be the double of the previous size. So it has a jump of the 2, and the recommended value for the any CFD simulation, that the ratio of the next volume should be the 1.2 times or 20% of the previous size. It may be in the decreasing sequence or may be in the increasing sequence. The size should not increase beyond the 20% value of the previous one. So if this one size is 1 meter, the next size should not be more than the 1.2, and the next to next should not be more than the 1.44. But in the case of octree, the one size is 1, second size will be the 2, third size would be the 4, 8, 16, 32, and so on. So this is not uh, this is not going to give you the good results. So that's why we will revert back to some other methods which can give us the better mesh resolution. So you can see here that we have the this type of mesh here. Okay, one more important thing here is that if you just rename these material points which are generated automatically, so call them the solid which is inside the sphere, and the second material point is outside, which is inside the fluid. So we call this one as a fluid where the flow will be moving. You can also put the material point with the same name as a fluid, because the the mesh which is the part which we are going to use for the solution inside the sphere is going to be done in the Ansys mechanical, or more precisely in the transient structural. So you can put this name anywhere where you feel the flow would be. So this location is not important, but it should be inside the fluid. It should not be outside the boundaries, and also it should not be inside the this sphere. So we are almost done. You can, to confirm that the fluid part is properly selected, you can change this. You can decompute the mesh, replace the old mesh. Again, you can check the cross section of the mesh to be confirmed that the no mesh is inside the sphere. Okay, no, now go back to the part mesh setup. This time I'm going to define the tetra width around the sphere. So I'll put the value of 3. This means that the size of a sphere, which is 0.004, the next 3 layers will be of the same size as the size on the surface of the sphere. So the volumes will have the same element size as the 0.004 for the next 3 layers. And also I'm going to define the tetra size ratio, that is the how the mesh should grow after the sphere. So after 3 layers of the constant size, the mesh next elements will grow at the size of the 1.2. This will increase the number of nodes in the vicinity of the sphere where we have the important flow features. So recompute the mesh. This time it is taking some time because now mesh will be somehow heavier because of these two settings, tetra width and the tetra size ratio. So you can see that we have the fine mesh now in the vicinity of the cylinder. Now just go and delete the volume mesh because the octave mesh has the very abrupt size change in the mesh, and the CFD solvers simply does not like them. So just delete the volume mesh. Now we will smooth the mesh to the some higher quality. The minimum quality needed is zero point 0.3, which is there, but we aim for some higher quality for the surface mesh. Okay, next loop is with the Laplace smoothing. The next one is without Laplace smoothing, and continue for the next 5-6 iterations with and without Laplace smoothing. The last one should be without the Laplace smoothing because the Laplace smoothing usually produce the low quality. But when we run them in the loop with alternative selection of the method without and with Laplace smoothing, they produce a higher quality. But the last one should be without the any Laplace smoothing. Click on OK. Okay, now go to the mesh. This time select the option quick or the Denali and compute the mesh. The problem with the Denali is that although it produces the high quality mesh, but it requires the surface mesh as an input. So now we got the surface mesh from the octave mesh. So we discarded the volume mesh, kept the surface mesh, and now this is going to be the input for the Denali mesh, which is has a higher quality than the octave. So now click on compute. You can see that the now mesh is very smoother than the octave mesh. So this is our final mesh, and if you want you can again run the smoothing. So if you want you can again run the smoothing on the volume mesh. Okay, with Laplace. Okay, we'll keep this quality up to here, that is a 0.44. This is a volume mesh we have, sorry, this is a surface mesh we have on the sphere boundary. Just save the case. Now we are going to output the mesh. So the first step is selection of solver, which is Ansys Fluent by default. Boundary conditions. So here we are going to define only the boundary types, not the values for the boundary conditions. So for inlet, define the velocity inlet. For the pressure, define the pressure outlet. For the sphere, it's going to be the wall condition. You can copy the boundary conditions here and you can paste to the similar boundary. So the wall has to be the wall condition. So just paste the boundary condition here. No need to create new one and get selection from the menu. Just paste the boundary condition. So you can, if there are the many boundaries with the same boundary type, so you can copy the boundary type condition and then you can paste them on the different boundaries. Accept. Now output the mesh. Just select the options, they come in front of you. Open. It's a 3D mesh, so click on done. Now mesh will be exported to the Fluent.